Okay, so the recording has started now. Let me share the file, then we can start. Oh, I closed the file. I have to open it again. So give me a minute. So I will send you this set of notes. I thought Tito had shared them with you, but that's fine. I will send them to you. So today will not be a very problem solving intensive class. We are just going to learn the basics about mathematics. We are going to put together the language that is normally used in mathematics. That is the idea behind this, so that you can be able to express yourself properly mathematically. Some of the things may be familiar, but we shall make them a little more formal. So what I need now is, can you confirm that you are seeing the screen?
I can see the screen.
Okay.
Yes, it's visible.
Good. So what you need to do also is try to be alert with your pen and paper. So if I say anything that is not on the screen, you can write it down. And note it down and use it. Or if you ask any questions that are not covered in the notes and you get answers, you're able to note them down. So we'll start with the definition of a set, because a set is the most basic object you work with in mathematics. You work with a set of some numbers usually, or some objects. So it's important to get this right. So basically a set is a well-defined collection of objects. Well-defined simply means this: by looking at an object, I should be able to quickly state whether the object belongs or does not belong to a set. So that's what well-defined means. There should be no confusion. If I look at anything, I should be able to tell whether it belongs to the set or it does not belong to the set. If there's confusion, then that may not qualify as a set. There are some situations where that confusion does occur, but right now we don't need that level of mathematics. We just need to work with what we call the naive set theory. So the objects contained in the set are usually called elements, right? So if I consider a set containing the integers, then the integers are the elements. The numbers, say like 1, 2, 3, -1, 0, all those will be the elements of my set. If we represent, there's this shorthand we have here. If X is an element of the set A, this is how we write it as a shorthand. So if I have a set containing say the following numbers, 3, 4, and 5, then I can say 3 belongs to that set. And this is how I would write it. 3, I have this quantifier. So this symbol here means X is an element of the set A. So a lot of the times this shorthand will be used. So if you have any questions, you feel free to stop me and ask. You just put on your mic and ask the question. So if you have a small set, you can represent them by just listing the elements as follows. So for instance, this is a set with only 3 elements. So you can just write them out like that. So how we represent sets is you use these curly brackets. You see? And then inside the set, you write out the elements. So here you can say 1 is an element of the set A, 5 is also an element of the set A, and 7 is also an element of the set A. Right? That's for small sets. When you have small sets, you can just write them out. If they are bigger sets, then this may not be very useful. But we'll see how to express. So if you have two sets, we can say that a set is contained in another set. So for instance, in this case, we can say A is contained in B if every element of A is also an element of B. This example will make it clearer. So we have this set A here and a set B. This first set A contains only 3 numbers, 1, 2, and 3. The set B contains 5 numbers, 1, 2, 3, 5, and 7. So every element you see in A also appears in the set B. You can see 1 appears here, it also appears here. 2 appears here, the same, and so for 3. So all the elements in the set A appear in the set B, and therefore we can say A is contained in B. So this is the notation we use for A is contained in B. So this means A is contained in B. Let me see if it may be possible to, I don't know if I need to do any writing so far. If there's any confusion, you let me know. It may be possible to set up the whiteboard on Google Meet to write anything that needs clarification. Is that clear so far, what I'm saying?
Yeah, you're clear, Crystal.
Okay. So here we are just picking up the language. Pay attention to the language and the notation that we use. So there are two things we have already said so far. How to the shorthand for saying an object belongs to a set A. This will be the shorthand. And to where we have a set contained in another, this will be the shorthand. A is contained in B. So two sets are equal if they contain exactly the same element. So how do you show that? For them to contain the exact cell elements, these two inclusions must hold. Everything in A must be contained in B, and everything in B must be contained in A. If these two inclusions hold at the same time, then those two sets must be equal. So anytime you want to check that two sets are equal, this is how you check. You check that A is contained in B. In other words, every element in A also appears in B, and you also check that B is contained in A, so that every element in B also appears in the set A. So you can also split a set into smaller sets, which is what we call the subsets. So for instance, you can use a property to specify the subsets. So if you want, for instance, this R here represents the set of real numbers. We shall cover real numbers later, so this symbol will it will appear frequently. So for now, just know that this fancy looking R represents the set of real numbers. We shall also define all these sets, the real numbers and so on. So you can define a subset of a bigger set using some property. So here you will use a curly bracket to enclose your set, and inside here you will have the first statement saying where the objects are coming from. So here we are saying we are picking elements from this set of real numbers. So all elements in this set of real numbers which satisfy this property. So this is the set of all real numbers which lie between 1 and 4, including 1 and 4. Right? So this is one way to denote the sets, by just the property that is satisfied by elements of the set. And now this one is a subset of the set of real numbers. This one happens to be small, so you can actually list them if you wanted to. So this is one of the small sets which you can actually you can easily list. So if you are to list them, you just put write out the curly brackets and the numbers 1. No, you can't write them out. They are not integers. It's an infinite number of possibilities. So this it's just an interval, right? You can't write them down. If they were integers, you could, but if they are real numbers, you cannot write them down. There's an infinite number of possibilities between 1 and 4. But this describes the set, so if you're given any number, you'll be able to tell whether the number belongs to this set or does not belong to this set. So for instance, 5 will not be in that set. So the other concept is the intersection of two sets. So we denote the intersection of two sets by this A, then an upside down cap, or U if you like. It looks like a capital U but upside down. So this means A intersection B. So we're about to describe what this means. So the intersection of two sets will be the set of all elements that appear in both sets. They appear in A and they also appear in B. They belong to both sets. That's what we mean by the intersection. So for example, if I have the set A, it contains this one. These are how many? 5 objects, A, B, C, 1 and 3. Then I have B, which contains some other objects, A, C, D, E, and 3. So the intersection of A and B, which is denoted by this, will be all the elements that appear in both A and B. So if you look carefully, you can see A appears here, it also appears here. So we shall put it in the intersection. B will not be the intersection because it only appears in A but does not appear in B. So C appears in both, so it must be the intersection. 1 only appears in A, it can't be in the intersection. D only appears in B. E appears only in B, so can't be in the intersection. So the next one will be 3, which appears in both A and B. So this A intersection B will only consist of these 3 numbers, A, C, and 3. And you will realize that the intersection of A and B is contained in both A and B. Are we together?
Yes.
Good. Yeah, so today is just a language. Please, I know you probably are looking forward to solving problems, but once you understand the language, it's much easier to go through the problem solving. So the next thing we talk about is the union of two sets, and how we denote it is this. The union of two sets is basically the same cap but now facing upwards. So a U facing in the right direction will denote the union of two sets A and B. So the union of two sets will simply be all elements that appear in either A or in B or both. So we use an example here. If we take the set A consisting of these 5 elements and the set B consisting of these 5 elements as well. They don't have to be 5, they can be more than 5, but this is just an example. And the two sets can have a different number of elements. One can have 20, the other one can have 5, and so on. They don't have to have the same number of elements. It just happens that in this example they have. So here we can write down all the elements that appear in A and write down the remaining elements that appear in B, which is A and B. So anything that appears in both A and B is listed once in the union of A and B. So for instance, K appears here, it also appears here. So we shall list it only once. And once you have listed the ones that appear in both, the ones that appear like, for instance, A appears only in B, so we add those as well. B appears only in B, so we add those as well. P also appears only in A, and we put it here. Anything that appears twice is listed only once in the union, and this gives you the union of A and B. Any questions on that?
No question.
Okay. So it's possible to, previously we have just checked the situation where we get the intersection of two sets. Now it's possible to get the intersection of more than two sets. So if you have several, for instance here we have 5, the intersection of all these 5 sets will simply be the set of elements that appear in every one of them. So you go through the elements and find which one appears in every one of these 5 elements, and that will be that element will be in the intersection of all the 5 elements. So you can extend this intersection to more than 2, to as many as you wish, even an infinite number. The same you can do for the union. You can extend the idea to the union of more than 2. So so there's one special set which we call the empty set, and the empty set is taken to be a subset of every set. So just take that one as it is. The empty set, any set will have the empty set as its subset. So that we'll take that as true every time. So anytime you want to list the subsets of a set, one of the sets you will list is the empty set. The other thing maybe I need to mention is every subset is also a subset of itself. So A is also a subset of itself. If A is a set, then A is contained in A, and therefore A is a subset of itself. So anytime you are listing the subsets of a set, you need to list the empty set, the whole set, and then all the other smaller sets. So the empty set, there is a notation for it. I didn't write it down, but when we need to, when we come across it, we shall write it down. I'll try to set up the pencil app so that tomorrow we're able to write. So we define the disjoint sets. Now disjoint sets are sets that do not have any elements in common. So that means the intersection is empty. Right? So A and B here are examples. 1, 2, 3 are the elements of A. A, B, C are the elements of B. They don't have anything in common. So the intersection is empty, and we say that these two sets are disjoint. So these are some properties of the union and intersection of sets. So if you we will not bother too much with this. Just try to remember them. If you get the union of any two sets, you end up with the same set. I mean, the union of a set with itself will just give you the same set, because you'll again list all the elements in A only. And it doesn't matter in the order in which you write this. The union of A and B is the same as the union of B and A. Also, the union of A and B, you can do this in any order. You could, if you're getting the union of 3 sets, you could start by getting the union of the first 2, and or you could start by getting the union of the last 2, and then get the union of that with the first one. So it doesn't matter in what order you do the union, you will end up, I mean, in what fashion. You can put your brackets anywhere. The same is true for this is now where intersection and union are used. So you have intersection here and you have union here. So this would be the same as getting the intersection of A and B first, and getting the union of that with the intersection of A and C. So this would be the same. Again, we shall not prove this. You are not expected to prove something like this in if you're going to use it, you can just use it. You're not expected to prove it. So since we don't have a lot of time, we shall not bother with the proofs. And then the last one here is, notice the order. Here the intersection is in the middle and the union is out. So if you want to work this out, you can first get the union of A and B, which is this first one. I believe you can see the mouse, eh?
Yes.
Yes.
Okay. So you can get the union of A and B first and get the intersection of that with the union of A and C. So you can split them like this. So these properties will all hold. So there's one more thing, maybe I will mention it later. So if you have two sets A and B, we define the relative complement of B in A as follows. This is a shorthand for that. So this means the complement of B in A. So that means we pick all the elements of A that are not appearing in B. Or rather, you knock out all the elements of B from A, and you're left with the relative complement of B in A. All this can be represented using diagrams. Maybe as we go along, we shall use diagrams. I've avoided the diagrams for today. Diagrams sometimes make it clearer. So the complement of B in A, or rather the relative complement of B in A, will simply be all the elements in A that are not in B. Remember, I told you that you can also describe a set using the property. So here you're looking for elements that are from A with the property that they don't appear in B as well. So when you see this symbol with a slash, forward slash going through it, crossed like that, it means X is not an element of B. So that cross means not an element. If without the cross, it means it's an element. So I don't know if I had an example. Yes, here is an example. We have A and B, and we want to get the relative complement of B in A, right? So we need to find all the elements that are in A that don't appear in B. So and this turn out to be just B, C, and 7, because A appears here. It also appears here. 3 appears here. It also appears here, so we don't need it. 9 appears in A. It also appears in B, so we don't need it. The only ones that we will need are the ones that are in A but do not appear, and that don't appear in B. So that makes our set B, C, and 7. So you could draw that in a diagram. These are the elements that are common to both A and B. That's how I've drawn them. Then on this side, we pick the elements that are strictly contained in A, but not in B. And on this side, the other elements that are strictly contained in B, but not in A. So the relative complement of B in A simply means you pick the shaded area. What I have shaded. That gives you the relative complement of B in A. Is it making sense so far? Are you still in the meeting?
Yes.
Yeah. Don't use the chat, because right now I can't see anything in the chat.
Yeah.
Okay.
Unless I go back to the browser. Right now I'm staring at my screen, so I can't see anything in the chat unless I go back to the browser. So just use your mic to speak. So here is one more statement. If you get the intersection of A and B and the union of that with the complement of B in A, you still get A back. You can see that straight from here. The intersection of A and B is this, and the complement of B in A is this one. So if you put these back together, you just get the set A. The set A is represented by this circle. So if you put these two together, you get the full set A. That is this property. The intersection of A and B union the complement of B in A will be equal to A. This, we may never use these properties, but it's just good to understand what they're saying. So these ones are De Morgan's laws. I need a diagram to explain this. I don't know why I did not include a diagram in this one. I needed to have defined the complement, or rather work with this in a setting where we talk about a universal set. Let me see if I can get the whiteboard to work. Usually if I can get the whiteboard to work, then we should be in business. So I'm going to start a whiteboard. I don't know if you can. Oh, still. Goodness, I have to share with people. Okay, let me see. Maybe I can share. The whiteboard. Can you see a plain screen on your side?
Yes.
Okay, so I'll try to work with this one.
Yes.
So I will draw a set. So suppose you have a big set, which we shall represent it using this rectangle. So this set will be usually the set of all the things you're interested in. So if you're interested in the set of all students from Nairobi School, this box will represent your set. But inside this, you can have some students who are in Form 1. So this can be Form 1 students. So let's call it F. And then you can also have some students who play basketball. So inside this universal set, you can have other sets of interest. So in this setting, you can, let me now set up another universal set here. If I have a set inside here, so this set, I call it A. Everything that is outside this set, all these, but within the universal set, you work within the universal set, but you remove everything that is outside the set A. So everything that is outside the set A is what we want to describe. That is called the complement of A, and we shall write it as A complement. So there are some books that will write the complement of A as bar A. So this is just notation, but when you're reading the book, of course, they will describe the notation they're using, so that will not be a problem. And then some books will write also, depending on what you're writing. Some might write it as CA. But I think we can stick to this as our notation to denote the complement of A. So the theorem that was appearing on the screen earlier was saying that the complement of A union the complement of B, I think it's supposed to be the same as the intersection of, you first get the intersection of A and B, and then get the complement of that intersection. You can try to play around with this and see whether this makes sense. So the complement of the union of the complement of F and B so the complement of F will be everything outside F, right? So that will be, if you were to work that out, it would be this set and everything. That's the complement of F, right? Now the complement of B, I don't know if I can change color. Yeah. There. The complement of B will be as follows. Everything outside B, right? So if you just want to use a diagram to show this, so if you get the only thing that is left out is the intersection of what is in the middle here is the intersection of F and B. In other words, in this case we had Form 1s and people who play basketball. So this is a set of all Form 1s who play basketball. That's the only set remaining. And so what we have shaded is a complement of this bit. What is shaded now outside is a complement of this intersection, which is what we have written here. So if you, the same way you can also check that if you have the intersection of the complement of A and the complement of B, then this will be the same. First of all, get the union. Now you, on this other end, you will first get the union of A and B, and then get the complement of that. So these two will give you the same answer. That is what was in the notes. So I will put this down and return the set of notes. So this is the part we've just worked on. The other thing is that's important is what we call the Cartesian product. If you have two sets and an ordered pair of elements AB, where A is picked from A and B is picked from B, then the set of all such ordered pairs will be called the Cartesian product of A and B. Right?
Sure.
Yeah, so that's what we mean by Cartesian product. So if you are to write it out as a set, A cross B will consist of all ordered pairs, where the first ordered simply means you maintain the order. The first element will always be from A, and the second element will always be from B. So once you have this, then this is what we call the Cartesian product of A and B. And in general, the order matters. The Cartesian product of A and B will be different from the Cartesian product of B and A, because they may contain the different elements. So the orders, because here we maintain order, if you change order, we might get different elements as ordered pairs. So maybe the last thing I would say before we move to numbers is as follows. Something that we need to talk about for sets. I need to share the board again. Oh, I need to activate the board first, and I can share it. My computer is a bit slow. So here is my board. I'm going to clear I'll clear the board. So anytime you have a set, we don't care about the order in which the elements appear in the set. So for instance, if I have a set with the elements 1, 2, and 3, I don't care about the order. All I'm interested in are the elements. So these two sets are exactly the same. How you order them does not change the set. Still the same set. So sometimes you may choose to order them so that it's easier for you to track what is in the set, but it's still the same set. It doesn't change. So we don't care about order. Order is not important when it comes to, we say order, we just disregard order. It's completely disregarded. So we can't have that. We don't care about the order. So that's the one thing to notice, to take note about sets. Then the other thing I had said earlier is that the empty set, usually the empty set is usually denoted by something that looks like that. O is supposed to be round, and then is the empty set. So that happens. Then the other thing is this is an empty set. What else do I want to write? We say that if you have any given set, doesn't matter what set it is, then the empty set will always be a subset. And also the other thing we said that I may not have included earlier is that's a subset. Every set is a subset of itself. That's the other thing. So those three things maybe are what I will write before we move to the topic for numbers. So now let's go back to the notes. So this is very important to understand the different sets of numbers. It can be very confusing if you don't understand the different sets of numbers. So we shall look at the starting point. The starting point is usually just the counting numbers, where you start counting from 1, 2, 3, and so on. And these are called the natural numbers. So that's all the positive integers. So this set happens to be infinite. So anytime you have an infinite set and you know the pattern, you can write the first few elements of the set and put these 3 dots to indicate that the pattern continues infinitely. So such a set is where you have an infinite number of elements is called an infinite set. The previous ones we have looked at are basically finite. In other words, they have a finite number of elements, so they're finite sets. So we have the natural numbers. So the next thing we look at are the integers. What makes us move from natural numbers to integers is because when you have natural numbers, there are a few things you cannot do. For instance, you cannot do subtraction in the set of natural numbers. If I say subtract 2 from 5, 2 minus 5 will not work, right? I can't find a natural number which satisfies that operation, 2 minus 5. So I have to expand it to the set of integers so that I include the 0 and the negative numbers so that I can now do subtraction. So in the natural numbers, what you can do comfortably is addition. Any two natural numbers you add will give you another natural number. You can also do multiplication. You can't do division either because, for instance, if you divide 2 by 3, you can't get a natural number. But now the integers expand our options. We are now able to do some subtraction. Still, we cannot do division. You can still do multiplication, you can still do addition, but we cannot do division yet because, for instance, if I divide 2 by 3, again, I can't get an integer. So what enables us to do some division are the rational numbers. So rational numbers are those that can be written in the form a over b, where b, both a and b are integers. So this symbol here represents the set of integers. I think we used it up here. This symbol here, it represents the set of integers. So rational numbers will be numbers that take this form. They can be written as a over b, where both a and b are integers, and b is not allowed to be 0. So if you want to write it in this notation, the set of rational numbers is represented by this fancy looking q, and it is equal to the all objects x which can be written in this form as a over b, where both a and b are integers. So the other characterization of the rational numbers is that if you write them as decimal, they will either terminate or recur indefinitely. So they have a recurring pattern, right? They terminate or they recur, and if they recur, there will be a pattern. There's the blocks of numbers that are keep repeating. Does that make sense?
Yes, it does.
Okay, so far you will have noticed that the natural numbers are a subset of the set of integers, and the set of integers is also a subset of the set of rational numbers. So integers are also rational numbers because any integer can be written as, for instance, if I pick 4, I can write it as what? 16 over 4, right? It's possible to write it in this form. It may not be in the simplest form, but it's possible to write it in that form. So any integer is also a rational number, and any natural number is an integer. In any case, we pick them from the set of integers. And then, as we have said, any rational number, if written as a decimal, it will either terminate or it will have a recurring block of numbers. So the one thing that now we cannot do with all the numbers that we have done is to get square roots. For instance, if I want the square root of 2, it does not fit in any of these categories. So I need to invent a new set of numbers, and that's what we call the irrational numbers. The other things also you can't get. So numbers like pi, for instance, will not fit any of the categories up there. So on those ones now form the irrational numbers. So these are the missing pieces to complete our set. So irrational numbers are the opposite of rational numbers. You cannot write them in this form. You cannot write them as a quotient of two integers. It's not possible. And sometimes this symbol doesn't seem to be any universal way of writing the irrational numbers, but we shall use this symbol I, this fancy looking I, to represent the rational numbers. So the rational numbers and do not have any numbers in common with the rational numbers. So these are the examples of irrational numbers: pi, 2, root 2, this Euler's constant E. We might learn about that later. The golden ratio phi, which comes from the Fibonacci sequence, or square roots of prime numbers, for instance, square root of 7. We've already written square root of 2, and so on. Those are all examples of irrational numbers. So anytime you write an irrational number in decimal form, then the decimals do not terminate. They keep going on and on. There is no pattern, and they do not terminate. So the difference between them and the rational numbers is, for the rational numbers, the pattern exists and keeps repeating. But for irrational numbers, if they can be written in decimal form, then the decimal will not have any regular pattern, but will also not terminate. It keeps going on and on, but with no regular pattern. So when you put all these numbers together, if you put the rational numbers and the irrational numbers together and get their union, you end up with a set of real numbers, and you can represent those with the number line. So what follows are just important subsets of the real number line, the ones that we may encounter from time to time. So here is a set of all real numbers which are strictly greater than 0. So these are what they call the positive real numbers. Positive means strictly greater than 0. Then the next one is a set of numbers, again a subset of the real numbers, which is greater than or equal to 0. So here 0 is included. Now this I usually call the non-negative real numbers. So non-negative means greater than or equal to 0. Positive means strictly greater than 0. So another way to write this set is like this. So this means the open interval. Open means both sides are, the numbers at the ends are not included. So from 0 to infinity. So this one is from 0 to infinity. Infinity is not a number, so we can't put a square bracket on that side, but on the side that is included we put a square bracket, 0. So this one is an interval of finite length and includes both ends, A and B. So this one is normally called a closed interval from A to B. So this is a closed interval from A to B. This one is an open interval from A to B, where A and B are not part of the interval. So that's why it's called open. Then the rest has different types. This is half open. It's closed on one side and open on the other end. This is also half open. And it's numbers between A and B, but not including A. Including B, but not including A. So this goes on and on. It's just playing around with a... Is this one repeated? Oh yeah, these ones were done. So these all numbers bigger than A. All numbers bigger than or equal to A, so including A. All less than or equal to A. So there are different ways to represent them, as intervals or as sets. So this side is what we call the interval. So at some point we'll be interested in counting the number of elements in a set, a finite set, and also the number of subsets it can have. So I will read this, but then I go back to the whiteboard so that I can explain this further. So if you have a finite set, then the number of subsets it can have, all the number of subsets can have is 2 raised to n. So this includes the empty set and the whole set itself. Let's do an example so that this makes some sense before we stop. So I bring back the whiteboard. Let me clear the frame. Okay. So you can see the whiteboard?
Yes.
Good. So if I have a set, I will use a small set. So I'll get a set with only 3 elements. The 3 elements, I will call them A, B, and C. So I can write down all the subsets of this set. For instance, I pick up all the subsets. They just contain only one element. So that will be A, B, and C. Right? Then I can now try to get all subsets that contain only 2 elements. This one is easy to write down, so we can easily write them. There's A, B. Then we have A can be paired with C to get another set with 2 elements. Then B can be paired with C to get the final set which has 2 elements. So the remaining ones will be what? The whole set is also a subset, so this is another subset. Every set is its own subset, so it must be counted as a subset. And then the only other subset we have left out is the empty set. If you count all these, you'll see we have 1, 2, 3, 4, 5, 6, 7, 8. But what is that? That is exactly 2 raised to 3, where 3 is the number of elements in the set. So if this is a set A, usually we denote the number of elements in the set. So if we put 2 straight lines around A, this denotes the number of elements in the set A. So this means this thing should be equal to the number of elements in A, which is 3. And then the set containing all these. So if I have another big set, which now will contain the subsets. So the elements of a bigger set which contains a subset is what we call the power set. So the power set is the set consisting of all subsets. So I would have to keep writing this until I end up. So I will avoid writing what is in between and just write the last ones, A, B, C. So here it's interesting because the elements of the set are also sets. And then the last one we have is the empty set. So this what I have written down here is called the power set. Usually they use some fancy looking P. So this is the power set of the set A. So the power set is a set consisting of all subsets of the set. And then what the theorem in this case, if the number of elements is equal to n, the number of elements in a set is equal to n, then the number of subsets it will have. So the number of elements in the power set will be this. It's hard to write on this screen, but I hope my handwriting is making sense. The number of elements in the power set will always be equal to 2 raised to n. When we are doing some combinatorics, we shall see how to prove this. There are ways you can prove it, but for now it's just important to use it as a truth. You will not be required to prove it. This is allowed. You're allowed to use this in the solving a problem without having to prove it. Is this making sense?
Yes, it is.
Yes, it is. Yes, yes. Yes.
Okay, so we'll stop there for today. Of course, today was just to get this language. We have not even covered everything about language. It's just some basics. Anything else we need, we shall cover it where we need it. So this was not comprehensive. It was just to give an introduction of the basic structures that we use in mathematics. So what time do you propose for tomorrow? 9 o'clock? Can you propose 9 o'clock? You can write the number for me here. I'll send.